Let's use implicit differentiation to study motion in 2 dimensions. So here we have a particle moving in 2-dimensional space. So there's my x-axis, there's the y-axis, and it's moving along the graph of y cubed is equal to x squared. Now you could solve this for y as y is equal to x squared and then the cubed root of that. But effectively, it's going to give you a shape that kind of looks like this. So we've got a particle traveling along this curve. Now we know that when it is at the point -8, 4, so over here at -8, apparently here's a y value of 4. In fact, let's just go ahead and double check that this point is actually on that curve. So if our equation is y cubed is equal to x squared and x is equal to -8, then I have a 64 on that side. And if y is equal to 4, I also have a 64 over here. So the equation checks out. So that is indeed a point on our graph. All right, so as the particle is right there, we know that it's moving 2 units per second in the downward direction. So that means we have to be traveling in this direction. Right? We couldn't be traveling in that direction because then we would be increasing. So we know as we travel along this curve, we're going in this direction. We're going to touch the origin, have a sharp turnaround, and go in this direction. All right, so the question is, what's the magnitude of that green vector right there? How fast are we traveling? And in what direction are we moving in the x-coordinate? Right, we know that dy dt is equal to -2 because we're traveling 2 units downward in the y direction. So the question is, what is dx dt? How fast are we traveling in this direction? All right, so obviously, and in what direction, we're going to get a positive number out of this because we know, as we've talked about, we're traveling in the rightward direction. So let's take our equation. We have y cubed is equal to x squared. And we're differentiating with respect to t. That's very important. You don't want to differentiate with respect to x because you're asking yourself, how fast am I moving in x according to time, right? So if I differentiate this equation with respect to t, I have 3y squared times a dy dt is equal to a 2x to the 1 times a dx dt. Right? Because neither of these variables, x or y, are the variables that I'm differentiating with respect to, I have a chain rule, a non-trivial chain rule. So now we can take this equation and solve for the part that we want. How fast are we traveling in the x direction? So let's move some things around. Dx dt can be solved for by taking 3y squared dy dt. So all of our derivatives are with respect to t. So I'm going to move to Newton's notation. So 3y squared dy dt divided by the 2x. Now we're interested in this particle at the point -8, 4, right, over here. So this will be 3 times a 4 squared over a 2 times a -8. And then the y prime, how fast are we traveling in the y direction? That was given to us in the problem, 2 units per second in the downward direction. So -2. And now we just have a bunch of algebra to solve. So we end up at 3 times a 16 times a -2 over a -16. Our 16s cancel. In fact, the negatives cancel. So we really just have a 3 times a 2 or a 6. All right, we don't have units, so it's just units per second, because those are the only units that we had. And notice that we got a positive, and we knew we were going to get that.